It's so small. It's nice. Usually, I see the 80s with like some big mouse, fancy mouse. Okay. Yeah. Let me know when I'm live, please. All right. Hi. Welcome to the fourth and final installation of our Back to School live stream series. Thank you for choosing to join us today. I'm very excited to have you. And if you like what we're up to, please don't hesitate to subscribe to the Ansys Tech Tips YouTube channel and like the video, share it with your friends. So today we're going to go over simulation for autonomous vehicles. Wildly interesting topic. It's really taken off lately. If you've been paying attention, you know autonomous vehicles are the next big thing, and it's not just cars. The ecosystem around autonomy is ever expanding, and there's a ton of interesting thought that's gone into how do you build these systems with more reliability, more safety, and fast enough to keep up with the demand. So I'm Jacob Gantz. I'll be starting us off, and then my colleague Jason Ballmer, an application engineer for Ansys, will be taking over for the technical portion of the conversation today. So a quick thank you to the Envision Maker Studio, without whom we wouldn't be having these kind of events, so thank you. And to the UCSD IT and AV services. So we'll start by giving an overview really of basically how simulation is leveraged in the autonomous vehicle ecosystem. And by the end of today, you'll also understand the resources that are available to academia, and that learning simulation in school is an attainable goal. And we're going to focus really on high-frequency electromagnetic simulation. So obviously with autonomous vehicles, there's a ton of stuff we could talk about. We narrowed it down to high-frequency electromagnetic simulation, and we specifically are talking about the Ansys tool HFSS. And by the end of today, it should be very apparent that if you understand how to innovate with simulation and you really build this skill set in school, you'll have no problem landing a job, and you'll be able to take this and launch your career. So if you missed our earlier 3 workshops, I encourage you to look on the same channel, the Tech Tips channel. All 3 workshops are now permanent videos. Please check them out, and you can watch them on your own time. We covered really a good chunk of Ansys technology in these 3 videos, and we're going to cover a lot more of it today. So if you want a more thorough explanation of Ansys tools, definitely refer to those last 3 videos. I'm going to kind of breeze through our introduction so we have more time for the technology today. But Ansys is leveraged throughout every industry. We're focusing on autonomous vehicles today. And a quick shout out, if you're a student team watching, we'd love to sponsor you. We sponsor hundreds of teams worldwide, and that includes software training and mentoring, throughout the process of you learning our technology and applying it to win cool projects and competitions. And we do this to help you land a job because there's a huge demand for engineers who can build things, and specifically engineers who can build them well using high technology and solutions like Ansys. Lastly, where do you go to learn Ansys online? HFSS, you can try out YouTube and check out the tutorials that are here from Ansys, PADT, and Simutech. And if you have a question on HFSS, you can go to the student community and ask it there. We're always happy to help, whether it's an Ansys engineer answering your question or some colleague from around the world who happens to be working on a similar problem. So if you don't have access to Ansys yet, there's a few easy steps you can take. First, ask your faculty advisor, your professor, your IT director. You may already have Ansys on campus. If you don't, in your student team, apply for a sponsorship. Get a license that way. Lastly, if you're interested in CFD, computational fluid dynamics, or FEA, mechanical simulation, we have a student product for you at ansys.com/student. And if you want to learn HFSS, if you want to get access to that, or Maxwell, or any of our electronics tools, for research, for educational use, for student teams, doesn't matter, click Contact Us on our website, ansys.com/student. This is my contact information. If you want to get a hold of me for any reason, feel free to give me a shout or connect with me on LinkedIn. And now I'm going to pass the mic over to Jason Ballmer. So Jason, like I said, he's a senior application engineer for Ansys, specializing in HFSS. And one more time, please like the Tech Tips YouTube channel. Please subscribe to us and like our video. Share it with your friends if you like what we're doing. And if you're watching and it looks a little fuzzy, upgrade your settings and make sure you're streaming in 1080p, because we are streaming in 1080p here. And enjoy. Thank you.
Thanks, Jacob. Thanks a lot for joining. I'm very excited to talk about this topic. So we're going to spend time, hopefully at the end of this, you'll get a feel for what we anticipate simulation and simulation's role to be in autonomous vehicles, and also be comfortable with running HFSS simulations and actually learning how to quickly in real time do pretty basic operations that can extend and scale pretty quickly. So the way we structure this talk is I'll give a quick overview of autonomous vehicles and focusing mostly on radar applications. And we'll go right into a demonstration. Just kind of hit the ground running with a simple antenna example that's pretty easy to construct. So we can highlight some of the features of HFSS and how it actually operates, you know, in a very real sense. We'll also give a good overview of simulation in general. I'm going to spend some time talking about finite elements and what exactly it is, and spend a little time talking about the workflow and components to actually make a simulation work, where we start and what the endpoint is. And then I'm going to end with a treatment of how to take a standard finite elements model and start to scale things up, and give a little bit of a background on the different types of solvers that we're using to be able to mix and make HFSS a lot more powerful in terms of being able to solve very large scenes that previously were not really possible. And then we'll finally end with a radar example as well. So if you were to look and walk around a modern vehicle today, there's a number of sensors and systems that you may or may not know about. This image here does a pretty good job of kind of breaking down the basic technologies by application. So you've got everything from adaptive cruise control and emergency braking, all the way to surround sensing, cross traffic alert, blind spot detectors. So you could have, on a modern car, it's very common to have a dozen or more sensors that are embedded around that automobile. And if you look at mapping those sensors, not only from function but by type, you can see there's kind of a wide array of sensors, everything from radar applications, which we'll be spending most of our time on today. So that includes long range as well as possible short range applications, as well as LiDAR, which is pretty common for things like emergency braking and collision avoidance. Cameras are certainly pretty popular. Parking cameras, backup, reverse systems. That's pretty common on automobiles now. And even ultrasonic sensors. So it's quite a bit of technology that needs to be integrated and handled responsibly and properly to be able to make decisions for emergency systems. And that's going to be even more important as we move into fully autonomous vehicles, as a lot of us are aware. So if you can imagine, so at Ansys, our job is to simulate as much as we possibly can. So imagine a scenario where I can, in software, lay out whatever my virtual scene would be. So in order to get the billions of driving miles that are anticipated to be able to field an autonomous system, we can create these virtual scenes in real time and actually run our simulated sensors through this environment. In this example, we're looking at a closed loop simulation where the scene is being rendered. The sensors are actually being
simulated as well. So actual physics-based simulation is taking place. And that perception is being made, the whole motion planning is being determined, and then motion execution is being fed back into the simulation. So what you're looking at here is what we would refer to as a closed loop simulation, where the simulated sensors that are getting the raw data are in a feedback loop that's actually, if you think of controlling the actuators of the system, it's part of that. So this is the vision that we have with all of those different sensor modalities, whether it's LiDAR or radar or even ultrasonic, to be able to get this capability, this simulation capability. And where we are right now, in this example, this is a radar example of that same sort of thing. This actually is an open loop simulation, where if you can look down in the bottom right of the animation, you've got what we call the ego vehicle. So that's the automobile that has the radar system embedded in it. And it's moving in this dynamic scene with lots of different vehicles in an intersection, things on side the road. And what you're looking at is a simulation of an actual radar sensor, the antenna, that is mounted on the vehicle itself, that is actually integrated and simulating that entire environment. And the image on the left is, you could refer to that as machine vision. It's a radar image. In this case, it's a range Doppler map. So we can look at the velocity of the targets that are found and see where they actually are in the scene. So that's the type of thing that we can do with a large-scale simulation. So I'm going to spend a little time talking about the ScaleUp before we get back to that scene, and I'll talk about it in a little bit more detail. If we think of the basic sensing element of a radar system, it's ultimately an antenna. So these are pretty common types of antennas that are used with these applications. So in this example, you're looking at basically a layout-based patch network. The transmit antenna is like a 1x5 array. We've got a receive element that's a 4x5 array. And they're sized differently. The shaping of the elements and the distribution and the number of those subarrays are going to determine the beam pattern and the characteristics of the antenna. So if I'm an antenna designer, I might be focused on trying to optimize this just from the pure sake of the antenna itself in a pristine condition to get the best performance I can possibly get out of that. And then if you look at the integration that takes place, I can continue to use simulation for that scale up. So in real life, I'm not just going to have the pristine state, but I'm going to have these multiple elements that are going to be integrated in some package that protects it from the environment. So that would be what we call a radome to keep ice and snow and mud off of the device. And then we start to integrate it on the vehicle itself. So these are all different levels of integration that are important that can all be done with simulation and help the designer, the antenna engineer, the automotive manufacturer help understand and make decisions about what system might perform better and what design decisions they might have to make in that process. So if you look at this example, this is a realized gain plot of one of those arrays. So this is basically a sweep in theta. So if we just look at the gain across a cut plane, we can see that the gain of this system peaks out at about 20 dB. So that might be a design metric that the antenna engineer was looking for. And the blue curve is showing the result of gain from just the freestanding antenna. But if you look at the comparison of all the different scale-ups, when we put it in the radome, and then we put it on the bumper and then behind the fascia, you can see the change of those values as it's starting to pick up different structures. And so the takeaway from this whole slide is if you look at the pristine antenna in blue and compare that to the red trace, you can see my ideal gain has been attenuated a little bit just from the effects of the radome and the installation itself. So losing about maybe 3 or 4 dB in peak performance, that might be a problem. You can also see the side lobes as a result of enhanced scattering from the unintentional beam. So those are typically things that you'd want to minimize. So this gives me a real way of actually looking at the effects of doing that large scale integration. And this is a pretty common thing to do with a scale up simulation. Okay, so I think now it's probably as good a time as any to do a quick demonstration so we can actually see the software in use. And I'm not going to do, for the sake of time, instead of doing a large scale high frequency system, I'm just going to do a very simple, kind of a canonical a dipole antenna. So I've got HFSS, or I have Ansys Electronics Desktop open right now. And I'm using something called our ACT extensions, our Ansys Customization Toolkit. A lot of the extensions that you see in my view right now come built in with the latest version of Electronics Desktop. If you were to install, those extensions are available. And I open up these extensions by going to the Automation tab and enabling the Show Hide ACT extensions. Okay. So the one that I'm using actually comes with the install called the Antenna Toolkit. So I'm going to launch that Antenna Toolkit, and these are a number of parametric antennas. So the idea is we can take some of the work out of building the detailed structure of your maybe complex antenna system by making parametric forms that the user just has to fill out. So if you look at all the different types of antennas that are in here, you could define a canonical, or I should say, a canonical corrugated horn antenna. You might have different types of patch antennas. So there's like elliptical feeds. All of these things are parametric. So you punch in the important parameters. Maybe it's a width, maybe it's a thickness, and other things, and then we basically set up the model like that. So I'm going to use a simple dipole. So I'm just going to go to wire dipole, and you can see my settings. I've got a center frequency, and I've got a dipole length, and I've got a feed gap. So those are some of the important things that I need to basically size my dipole so that it's resonating at the frequency that I think it will be. So this is like a half wave dipole. So I'm just going to leave all the default settings, and I'd certainly encourage people to go through this. When I say finish, you can see there's lots of things that are taking place in the background. And that's where, the ease of using the Antenna Toolkit is that all of the HFSS setup is being done for me. So even if you're an antenna designer and you're probably going to be using much more complicated systems, sometimes it's nice to be able to see what similar type systems, what kind of settings we sort of recommend in the background for these sorts of things. So now I've got a geometry here that you can see. I'll go ahead and close my ACT wizard. And I'm going to go through this in a little bit more detail as we go through the lecture part. So I'm just going to walk through a basic simulation right now. I'm just going to hit solve. When I go to the simulation tab here, I can validate my geometry. Typically, that's a common thing to do, just to tell you if there's any warnings, if you've got overlapping geometries, if you've got materials or some conditions that were not set yet. In this case, when I validate, everything comes back clean. It tells me my 3D model is okay. My boundaries and excitations are all set up. And I'm going to close that, and then I'm going to disable one of the settings that was put in here. And I'll explain the solution setup actually after the fact. So I'm going to disable this one sweep right here, just for the interest of time, and then I can go and analyze this geometry. So lots of things we're going to talk about what's going on in the background here. It's you'll see some messages about adaptive passes. We're going to spend a little bit of time talking about that. And basically that's a way to guarantee that we're getting an accurate solution. So it pertains to mapping our geometry into what we call a mesh. And we'll spend considerable time on that. So this solution solves pretty quickly. And you can see I've got a bunch of built-in reports already. So I can double-click the first one, which is a 3D, what we call a 3D polar plot. So if I just double-click that guy, I'll get a new view. And you can see that's what you would expect from a dipole. It's a donut radiation pattern. Really no controversy here. There's a bunch of other report types that are set up. If I go to the results tab, all of these things are at my disposal now. So I could do things like terminal solution. I can do contour plots. I can do modal solutions. If I was doing an emissions test, like a EMC or a radiated frequency emissions project, I could actually set up emission data and look at where my violations occur. So there's lots of reports, and I'm really only touching on just a few that are pertinent to maybe an antenna design. But I could look at the far field gain pattern, and I could, typically an antenna designer, one of the first things they go to is something called return loss. So this is a measurement in dB, and it's basically characterizing the performance of my antenna at my intended frequency. I didn't spend much time on it, but the toolkit defaulted to 900 megahertz. So I can see if I get good return loss for my S parameters at 900 megahertz, then I know that I'm not getting reflection set up and the antenna should be radiating. There's other ways to evaluate it as well. So in this case, return loss well below 10 dB means I'm in pretty good shape, and you would not expect it to radiate much outside of that band. Okay, so I'm going to do kind of a scale-up analysis and show how we're going to come back to the radar story a little bit later, and we're not designing radar systems with 900 megahertz dipoles, but what pertains to this simulation is very relevant for any type of radar simulation as well. So what I want to do is kind of show some of the different capabilities that we have in hybridization. That was a finite elements model that took place with the boundary condition. And if I go and look, what I'll do is I'll save this model. And if I go into my HFSS menu and look at solution type, I can see down here towards the bottom with these driven options, I've got something called an auto open region. I'm going to toggle that off just so we can see what it is. And notice here's this volume that shows up. That's typically referred to as an air box. In this example, we assigned an open boundary condition to it. So this is important to show how we're able to start to hybridize solvers. If I choose a different type of boundary condition that we'll learn about in a little bit, I'm able to take that result from this simulation and actually connect it with what looks like a completely separate air box. So what I'll do here is I'm going to go ahead and I'm going to build a new box. So I'm in my draw view, and if I go to draw a box basically, I'm going to say it's okay to remove that solution. And I'm going to sketch a new air box. So if I pick the corners in a plane and I can scale up to the top, I've got a new component here. And notice when I go to vacuum, I had my former radiating surface. I'm going to delete that now. So now I have this new box that has not been assigned a material. So now when I assign that material, it automatically defaults to a vacuum. I'm going to let me actually change the color so I can see through this thing. So if I click on the object itself, if I click on the new air box, I can look at my properties window down here. I'm not sure, depending on how you've set up HFSS, your windows could be in different locations. I make mine default down to the bottom left corner. So now whatever I select over here, I can make changes. And I'm going to go ahead and change the color to something that might look a little bit more like a blue sky, telling me that it's air. And then I'll change the transparency so that I can see through it. Okay? Now, with that, I'm going to select that new box that's been assigned vacuum, and I'm going to right-click. And when I right-click, I get a number of things that pop up. What I want to do right now is assign a hybrid region to it. And I'll explain this in a little bit. So I just want to go through the motions of the simulation right now. I'm going to assign something called the FEA boundary. That stands for Finite Element Boundary Integral. Okay? And when I do that, I get a confirmation. I can name it whatever I want. And I'm going to select OK. And I'm going to rerun this simulation. If I go up to my simulation tab, I can verify that I didn't miss anything. And I'll go ahead and analyze again. It's going to go through that same, what I call the adaptive mesh process. And in the first simulation, I ran something called radiating boundary condition. Well, this FEA boundary is considered to be a hybrid condition, but it also mimics a perfect absorber. So it's essentially running the same simulation, but it's going to come with some additional benefits that we're going to go over. So if I go verify my return loss, I can see I'm still getting pretty much the same thing. It looks a little bit different, but it's actually really similar. So my return loss looks good, and it tells me that I have a decent boundary and I'm not picking up any artifacts. So now the benefit of using this different boundary condition, I'm going to demonstrate by kind of scaling up my simulation here. So notice I've got one project open with one design type in it right now. Well, it's pretty convenient if I just right-click and copy that and then paste it into the same design. Because here's where I'm going to start doing ScaleUp. What I'd like to do is I'd like to mimic this antenna. I just want to copy it. So the first thing I'm going to do is create a local coordinate system. So notice I should still be in the draw ribbon. And when I go up to this icon here, I'm going to say offset. And offset is asking me to choose a location where I want to put the next coordinate system. And in this case, I want it to be maybe 100 millimeters or so off of the Y coordinate. So if I hold my Y key down, I can see as I slide it, I get feedback on where that next position is going to be. And when I see it show up at 100 centimeters in this case, I'm just going to go ahead and click. So now if I expand my modeler tree here, not only do I see my geometries with materials assigned to it, and I can see this sheet, which was a lump port, I can also see I've got this new relative coordinate system. So now with that, I'm going to box select that antenna. I'm going to copy it. And now I'm going to paste. Actually, I think I can just do so Control V works just fine. And now by doing that, I can see that now I have two excitations. I didn't spend much time talking about excitations, and we'll cover that too. I also have two FEA regions now. So I'll validate this model, and now I'm going to analyze it as well. So a couple things you'll notice in this simulation is that I've increased the size of my simulation. I've added an additional port. I've added the additional antenna. And for that reason, would expect it to be a longer simulation. And when this is done, I'm going to be able to look at the coupling between these antennas. And we also get feedback about these different domains that are being set up and solved. And I'll spend a lot more time talking about that after we go through the quick demo. So if I go to the Results tab, I can go to Solution Data. And I can see I get a full report on everything that's taking place in the background. So I can look at my profile for the simulation. I can look at convergence, which we'll spend a lot of time talking about what convergence means when it comes to the error of a simulation, and any of the detailed matrix information that I want from that simulation. And antenna designers are typically using S parameters freely. So S parameters are a way of characterizing reflections for not only return loss, but for coupling between antennas, so one device to the next. So a transmit and a receive array, that scene can be characterized through S parameters. So we go through that simulation. And when it's done, I can now look at something like the coupling. So that's S parameters, but I'm no longer looking at the return loss that defines whether or not the antenna is radiating. I'm looking at the amount of energy that comes from one antenna to the other. And that's my coupling. So I can see this is a very different curve than what I saw before. We're still solving for the same range of solution, but I can see that my coupling is significantly higher when I get to my resonant frequency, because both of these antennas are actually, resonant at this 900 megahertz frequency. And everything else outside of that is going to be out of band. So you'd expect a significant amount of attenuation. So I can continue on with that. And now I can start looking at what happens if I have scattering environments in between. Because in real life, it's not just going to be a transmit antenna and a receive antenna for the radar. It's going to have to interact with lots of scattering devices. So I can quickly create a planar geometry. So I'm just going to make a simple plate. Choose my plane appropriately. And I can just use the drawing tool and just put a metallic plate in here. And if I can just, I'm just going to use the box as a template. And now that I have this plate, I can assign something called a boundary. So instead of assigning a hybrid region, I'm going to assign this metal plate a perfect electric conducting boundary. Now I can select that object, and if I move it, I can define a vector and select the reference point, and by holding Y, I get to place that plate, excuse me, wherever I want. And now I'm going to assign an additional region on this, and this is going to be called an IE region. And if I verify that solution, I can analyze. And now, not only is it solving for the two antennas in free space, but it's also accounting for that metal blocking structure that I have between the two antennas. So it's a very simple example. But it's representative of everything that I would be encountering if I was to install and field an actual radar system. If I give that a second to complete, I can look at the effect of that blocking plate now. So now, sweeping over the same frequency range, all of a sudden I'm not coupling nearly as good as I was, which makes sense because I've got this metallic blocking structure in front, but it's also producing lots of energy around it for the coupling in the form of diffraction. So it's not completely blocking this plate, and it's actually able to wrap around it. So I still am actually getting a pretty decent amount of coupling through this, even though I've got this physical structure that's actually blocking it. So that's kind of a really quick, crash course and a walkthrough on how to do a simple, simple workflow operations, building up an antenna, being able to replicate objects, show how I can get coupling between these two devices and get S parameters, and account for some other scattering structure. So I'd like to spend a little bit more time going through what's actually taking place kind of in the background there. So I'm going to spend a little bit of time talking about finite elements in general. So the best place to start is with Maxwell's equations. So the first two, the divergence equations, are defining the fields that are emanating away from that charge source. So Gauss's law is relating the electric flux density to the volumetric charge distribution. The second one is claiming that there's no magnetic monopole. So this explains the fields that are emanating away at all times from that source. The other two equations at the bottom are the curl equations. So you've got Faraday's law and Ampere's law. And those are relating the electric fields and the magnetic fields, or the flux densities, in terms of the curl. And if you think of the curl, that's fields are actually curling around some structure. So what the third equation is saying, what Faraday's law is saying, is that there's a curling E field if there's a time varying magnetic field, or a magnetic flux. So just by generating a variation over time in my magnetic field, I'm actually able to generate that curling E field. And similarly with the magnetic fields, I can correlate a curling magnetic field to these current sources. And one of those is the conducting current source, and the other is what we call the displacement current. And if you take those two equations together, you can go through the derivations and show how they're coupled to actually explain radiation of electromagnetic energy. The two terms on the right, I tend to use the flux density and fields interchangeably, and that's not technically correct. They're simply related by material, we could call it material characteristics. So permittivity and permeability are ways of defining how these fields are going to interact with structure from an electric and a magnetic standpoint. So what we do with finite elements, we can solve these in the time domain, or we can solve these in the frequency domain. With HFSS, we do both. I'm going to take you through very high-level derivations that get us down to the frequency domain solver in HFSS. So this is time harmonic notation. Actually very similar to what you saw. These are all coming out of our manual. But I can see the relationship is preserved between the electric and the magnetic field and those current sources. So HFSS is often referred to as a field solver because ultimately we're solving for those fields, the electric fields, from a number of known sources that you see on the right-hand side, and then we can get the magnetic fields from those electric fields. So it's a correct representation to call it a field solver. Now, going over lots of work to be able to get to this, it starts to deviate a little bit from what we saw on the first slide. But it's actually a very similar form. And we're trying to get this to the form that a computer is going to be able to solve numerically. And if we go through some theorems and evoke some, I think, some green principles in here, we're able to reduce this down in terms of basis functions or weighting functions. So we can multiply the fields by these W's that you see here, which are the basis functions. And those are the things that we're ultimately trying to solve. And they are set to a single element of the complete solution space that we're actually solving with the FEM method. So these basis functions are ultimately trying to estimate the field behavior of any given cell within our larger volumetric solution. And if you keep deriving this down, we can get to something that looks like this matrix form, this simple AX equals B, where B is the knowns for when we set up our problem. For our dipole, it included a port inside that antenna. And A is representing that matrix that has the relationships between all those individual elements inside the solution space. So if I can solve for X, I'm ultimately going to solve for the fields. And that's the beauty of getting it into this matrix form, because this is what, at least for our direct solver technique, which is one of the solver techniques that HFSS uses, it's able to use some common solver methods like LU decomposition and Gaussian elimination to flip a really big matrix and then ultimately give us those fields. So if you can get that matrix inverted and start back solving for the unknowns, solving for X4 is going to give us X3 and so on and so forth until we get the entire set of fields for all of those unknowns solved. And that's the beauty of the finite element method, is that this really lends itself well to going to a numerical simulation solution on a computer. So the tetrahedra is where those basis functions are applied. So if you think of a basis function, it's basically a polynomial, and we can solve any number of combinations of orders of basis functions on top of any given tetrahedra. So the benefit of choosing one type of basis function over another might be a more accurate representation as the field varies from one part of the tetrahedra to the next, but it might come with a cost of maybe longer computation time. So sometimes going to lower order basis functions enable me to solve faster sometimes, but maybe I need smaller elements to be able to get that simulation. So you can see the scale is going from something like 6 unknowns for a 0 order, or a first order is going to be 20 unknowns, and a second order is going to be 45 unknowns, depending on what part of the tetrahedra is being solved for. So if I can explain that in a one-dimensional sense, we can say, here's a function for us right now. It's an E field. We want to solve that function over some space. If we divide this space up into cells, we can assign a polynomial that's going to try to represent that field characteristic over just that local cell. And we can solve for locations along that polynomial. So in this example, the red is the function that we're trying to solve, but the way that we divided up the problem, we're doing a piecewise solution for each cell. So those blue curves are representing an approximation to that function over the region of the cell itself. And what we're doing with the FEM solve is we're actually trying to minimize the error. So when we actually run the FEM simulation, we don't know what the value is, but we followed the Maxwell equation derivation to get us to this point. So if we can find a way to compare the real solution to the approximated solution, we can get this error. So the error is just the difference in how, it's a measure of how close we were to that simulation. And you can see in some areas, the error looks really good. We got a really good approximation of it, and in other areas, not so much. So one thing that you could do with this first cell is I could maybe change the order of basis functions, or I could divide it up into smaller cells. And I could do both. I could also change the order of the basis functions as well, right? And by doing that, I'm trying to get a better piecewise approximation in that area to be able to approximate that function. So I can chop it up in smaller cells, or I could go back to the original cell and increase the order of that function until it matches it better. And by increasing the order of the function, that means I have to solve for more unknowns, and that could be fine, or it might be something that I want to avoid. So there's many different ways to approximate that solution just by using simple polynomials and being able to divide them up properly and assign them properly to parts of the original geometry. And that's what the mesh is. So the mesh's job is to take those basis functions and apply it to the individual, tetrahedra across the entire geometry. So we usually start with some model of interest. In this case, we've got a helical antenna on a ground plane. We take that geometry, we put a mesh on it, and then we start to solve the basis functions that are on that mesh. And the mesh can get pretty complex. So it's very important to have an accurate FEM solution, to have a mesh that actually represents the geometry properly. And as you can see, if you're trying to represent things with arbitrary tetrahedra, you might have to get a very refined mesh to be able to represent some maybe high fidelity curved structure and things like that. And we have ways of doing that. So in this example, you can see the feed is coming through that, the feed hole where the actual, radiating element is being excited there. And it's a much denser mesh in that area than it is in other places. So if getting the mesh is right, if getting the mesh right is important to us, yet we're starting with a geometry, and you don't want to go through all of that, mesh building yourself, you need a process and some sort of criteria to tell you how to apply your mesh and when it's good enough. And the way we do that is with a technique called an adaptive refinement process. And the way that typically works is that we start out with our geometry. We'll generate an initial mesh. The initial mesh is taking all of our geometry based on the material references that are assigned to it and dividing the boundaries of the mesh based on the geometry. And now we go through a process where we try to minimize the error by increasing the mesh or changing the basis functions or both until we're happy. So we need to have a criteria, and that's when we say it's converged. When we're happy with the error has been reduced and it meets our criteria, then we're calling that to be a converged mesh.
Is that process automatic, or how software?
Yeah, so we're actually going through an automatic process. And if I can just go through that, we start with the geometric mesh, like I mentioned. We kick off the adaptive process, and when that solve starts, we're comparing the original geometric mesh with the second mesh that we run through that cycle. So we go through a solve, we compare it to the first mesh, and we look at, in this example, we're looking at S parameters. So we say, are the S parameters within the particular criteria that we looked at? If not, if it violates it by 2% or whatever, 1%, whatever it is, we actually go back through that mesh refinement process, and we come back and add additional meshes, mesh elements, or maybe change the ordering of our basis functions. And by the time we see that our S parameters are stable and they're no longer varying, then we actually call that a converged mesh. It met our criteria, and then we have a meaningful simulation model that we can trust.
By the way, I think we're holding questions until the very end. I think we're holding, yeah, thank you.
So to tie all this together, we talked about the basis functions. We talked about the tetrahedra and the mesh and the convergence criteria. If you look at this comparison of using different orders of basis functions on this particular patch problem, our metric here is the return loss. We can see the S parameters. They all look very much the same by using these different combinations. But if you look at the tetrahedra with the 0 order, we've got almost 500,000 elements. That's important because that drives the RAM utilization. So our RAM in this case is almost 3 gigabytes. It took 21 minutes to solve with 16 adaptive passes. Now, if I run that with all first order elements, I can see that I'm getting the tetrahedra down quite a bit. I'm also reducing the RAM requirement quite a bit, which means my solution time is also going to come down. And coincidentally, my adaptive passes have also come down. And if you continue down this line, you can see that trend. Going to second order actually increases my simulation time and actually brings my RAM utilization back up. But I was able to get by with fewer tetrahedra, and there might be a benefit for doing that. But what's really nice is that I can use mixed functions, and I can let the algorithm make a decision of what basis functions I want. And it's going to put them in the right place. So you can see, this is the one that really optimizes everything. By using the mixed order basis function, I've got the smallest of everything. Solution time has gone from 21 minutes down to about a minute, and my RAM utilization is like an order of magnitude down. So it's a pretty nice feature to be able to let the software do all that work for you, and that's what we're doing with HFSS with our implementation of FEM and everything behind the scenes. So you know, it's a comprehensive interface that does lots of things, including those maybe what seem like esoteric settings that can be very important. So we have algorithms behind the scenes that can do a lot of that heavy work for you. So just kind of a recap of the workflow, and we did a little bit of this. I breezed over a lot of this when I did the initial example with the antenna. But you know, a lot of workflows, if you look at our project tree, they're not always, you know, top to bottom, but they tend to generally follow that process. So I'm just dragging, in this case, that patch antenna and kind of going through some of the important elements of a typical workflow. The first thing you saw me do some of this is obviously the geometry. There's a number of ways to get geometry into HFSS. There's a pretty sophisticated set of drawing tools and capability that's inside of HFSS. So I can define things like, function-defined surfaces. I can turn that, you know, if I had something like a reflector antenna or something, so I can shape my pattern based on these equations. I can also turn those into solids by doing extrusions. You can see I can do Boolean operations. I can unite. I can subtract. So lots of capability inside the geometry engine of Electronics Desktop itself. You're also free to bring in external files from other, you know, CAD engines. So you can do direct links with just about any other CAD tool that you might be using through a number of different formats. Some of the proprietary formats as well as the neutral formats. And when that geometry comes in, it's your job to then start assigning the appropriate materials. So every one of the elements that you see in the CAD here has got some background material. So if you look at the substrate in this case and look at that material characteristics, you'll find in this case it's probably pretty simple, something like a dielectric loss, maybe a loss, some loss tangent might be defined. And you could add frequency dependence and all kinds of different material handling capabilities in there. You could put tensors in there. So that's the first step of a simulation, is to bring in the CAD and then assign the material properties. Boundary conditions. Some boundary conditions are similar to material properties in their application. Others are very different. If you can see the different types of boundary conditions You can see here things like layered impedance boundary conditions, lumped elements. In the example here, you're seeing two different types. We've got a perfect electric conductor that we actually use in the earlier simulation. You also see that radiation boundary that I talked about. So the bounding box for that antenna that has some 3D geometry as well as 2D sheets with perfect boundaries on it is embedded in this air box that's a radiation boundary. So that says that when we run that antenna simulation, it's treating it as if it's in free space and it's allowed to propagate freely. Excitations, when we talked about that big matrix, you know, AX equals B, the excitations are going to be the knowns that we have set up on the right-hand side. There's many different ways to excite a problem inside HFSS. If it's an antenna, you're typically giving it like a wave port or maybe like a lumped element with a terminal port. In this example, we're doing a lumped element that's a terminal. You can also see, you can do linked fields. I could do voltage. I could do incident wave excitations. I'll actually demonstrate that on one of our scattering problems coming up. Some of the things we talked about that I really breezed over in the initial demonstration that I just talked about are showing up in the solution setup. So we talked about the adaptive passes and what that is. The user is able to set those. So, you know, a typical thing to do is just to set a high number of adaptive passes to guarantee that we get this thing called convergence. And then options on choosing my solver type. Breezing over lots of things in this overview, but direct solver using, you know, mixed order basis functions or first order. There's iterative solver techniques that maybe sometimes helps save RAM utilization. Sometimes take a little bit longer, but maybe your main focus is reducing the amount of RAM. And then domain decomposition methods actually allow you to chop up one problem on multiple computers. So maybe you're simply running out of compute resources. You can divide a problem up, and that matrix is even getting divided up in a FEM solution as well. And it gets solved, different portions of the matrix are being solved, and they're all being brought back together. So there's multiple techniques to be able to use for that FEM solution. We already saw some of the results, you know, different options. You can do polar plots and other things that you can do with an antenna is, you know, some of the metrics that you want to use for antenna design, you can get those reported to you directly. So HFSS will you know, pull the important information, something like a peak directivity. You might not know where exactly it is. It'll actually pull that value for you. Something like a radiation efficiency. Those things can actually get calculated automatically for you if you look at calculating antenna parameters. So you know, kind of downstream important information that that you have access to. So doing pretty good on time here. We do have a demonstration that is starting to tie together. I guess I'm going between two different extremes here. We started with the talk on autonomous vehicles, and you saw the types of things that we're using simulation for that pertain to radar. So I spent a lot of time talking about a finite element solution, which is applicable to high fidelity, very complex antennas, even though we didn't solve complex antennas today. But what I wanted to demonstrate after going through some of those simple scale-up exercises is some of the techniques that are used in conjunction with finite elements that enables us to take an antenna module and then put it in a realistic scene. So if you look at that range Doppler map that I showed earlier, you'll have an understanding of how that was done. And all that stuff was done inside, you know, this one interface, being able to use a mix of tools and different techniques. So that's what I'm calling the scale up. Let's take what we know about a FEM solution, and now I'm going to start mixing different solution types and show you how you can scale that up. And to put it in context, the way that we think about solving problems, you know, numerically with our tools is based on electrical size and complexity. So you already have a really good overview of finite elements technique in HFSS. and you got to feel for the types of things it can solve. Those, maybe complex radome with embedded antennas, feed structures, waveguides. These are things that are generally electrically small. So think of things that are, maybe like a dozen wavelengths or less. When you start to get to larger and larger geometries, as you saw from the examples that we did with the different basis functions and mesh sizes, your RAM utilization is really going to start to go up. As you start to chop up larger and larger spaces, as tetrahedra start applying those solutions on these very large spaces, things can really grow. You can run out of RAM pretty quickly, and your simulation time might take a very long time. So there's many different techniques that we can start coupling with finite elements. So there's something called integral equations, or it's also referred to as moment methods, which is a pretty common technique. It's very applicable for larger bodies that are they're called open radiation. In this example, we're using it for a reflector antenna. So when you start to get above sizes of maybe tens of wavelengths, it's probably a good candidate to move from a FEM solution to a moment method solution, because it's still a full wave simulation, just being applied a little bit differently, and it gives us the advantage of being able to solve much quicker with smaller resources. We can extend even further by using ray tracing, which is really trying to do the same thing. You're trying to get larger and larger geometries, but instead of solving that entire domain, we're with a FEM technique or even a moment methods technique. We're applying different principles that are physical optics based to be able to solve these extremely large scenes. And what we're doing at Ansys with everything inside Electronics Desktop is we're trying to give you the options to hybridize and use the best solver for the best part of the job. So if you have a very complex structure that calls for finite elements, use a finite element solution on it. But if my scattering geometry in the background is better solved with the integral equation technique, as you saw from my earlier demonstration with the dipole, give me the ability to solve a FEM solution and now couple it with the integral equation solution and get the coupled response for that. And that's exactly what we're doing as we start to integrate more and more of these techniques. So we talked earlier about we could certainly be doing this in transient. We're doing this walkthrough using our frequency domain solver. And if we stay in the frequency domain, it's really easy to start connecting some of these different techniques. And I can move from what I'm calling full wave solvers, where we use those matrix approximations of Maxwell's equations, to asymptotics, where it's not a direct solution to Maxwell's equations, and it comes with some stipulations that we'll talk about. You've already learned about finite elements. We're going to talk about how to group finite elements in moment methods together with this thing called the FEA boundary, finite element and boundary integral equation. And then we're going to use that as a pathway into these different techniques like physical optics and shooting and bouncing rays. So that finite element boundary integral boundary that I put on our dipole antennas, that's really a big enabler to being able to do these large scale hybridizations, and it's very important to be able to understand what the value is of doing that. So let's just very quickly go over what moment methods does, and I'm not going over any of the equations at all for this, but it's really efficient for large classes of problems that are considered to be open problems. And what it does differently is that it's actually solving currents on dielectrics and conducting body surfaces. So instead of doing a volumetric solve, it's just looking at the surface currents on the object. But it still takes into consideration the material characteristics. And only a surface mesh is required, so that really helps us. So antenna placement is really, with a discussion today, that's really a big application for integral equation or moment methods techniques. I use the term interchangeably, and a lot of other people do. So an example of, I guess, a comparison for this simple blade antenna, I can see I've got an HFSS finite element solution of the same exact thing using an IE solution. We can run that adaptive mesh process, and when we get to the end of what we're calling a converged mesh, even though they deviate in the beginning, they ultimately end up at the same place. So I still apply my adaptive mesh process like I was showing for FEM to my integral equation domains as well. So finite element boundary integral is it's another absorbing boundary condition, but what's unique about it is that it builds off of some of the earlier absorbing boundary conditions that we've implemented in HFSS. And the really important thing here is I guess there's a few important things about it, but to start with, just treat it as if it's a perfect absorbing boundary condition that comes with some benefits. So what ultimately is happening is that a FEM solution, just like we talked about before, is taking place inside that volume, but it's also considering the bounding box fields. And if it has the field solution of that, we can use the Huygens principle. That means that if we have a very complex representation of something that took place inside, if we can characterize everything on the surrounding boundary, we have a complete description from the standpoint of anything that takes place outside of that geometry. So whatever takes place inside is completely characterized if I give it a FEA boundary. And some of the benefits of that is that it's also referred to as an exact transparent condition. So there's no theoretical limits of how close that structure can be on the dipole. So what I'm comparing left and right here is one of the earlier implementations of an absorbing boundary condition is that radiation boundary. It comes with some constraints. I can start to get numerical artifacts if I don't implement it properly. If I have grazing angles that might be coming off of a boundary edge, or if I just make that box too close to the radiating structure, if I look at the variation of my S parameters, when I change the size of that air box, my absorbing boundary condition can change quite a bit. Excuse me, but notice it's really unaffected when I look at my FEA region there. So that's a huge benefit, because now I can start to shrink my space around these radiating objects. I'm saving my mesh. I don't have to mesh as much volume around it. Some of the other benefits that I get is arbitrary shape enclosures. This example are just showing rectangular boxes. Some of the techniques are limited to these rectangular structures. With the FEA boundary, I can get very creative about how I cut out my geometries around these radiating structures, and it allows me to do that. And that's really one of the big things. And the largest thing is that it allows me to communicate information from one region to another region. So a good example of that, even though this is just a finite element example, the first solution, this is an immunity test. So we've got a vehicle and we want to expose it to some radiation to see if we can disrupt the electronics. So a pretty standard immunity test. And this was actually some study that we did with our colleagues at Fiat down in Brazil, and our channel partners ESSS, which is also available on our website. I would recommend looking up this Ansys Advantage article. If you look at that first solution, that's a full FEM solution where we're actually including the horn in the space with the automobile, as if we're in an anechoic chamber and we're running this test. And I can get the exact same result by chopping both of these up into these FEA regions, and the benefit is just the speed of it was a tenfold improvement on simulation speed and then the reduction of RAM. And notice the cutout on the vehicle is actually one of these shell cutouts. So if you can get creative with how you hollow out your geometry, FEA's fine with that. So you're able to save even more by not even modeling the interior of the vehicle. If I only want to model where the wire harness might be running, then that's the only place that my FEA region needs to cover. So that's an example of very similar to what I did with the two dipoles. I'm linking two FEA regions together. This is just a lot more complicated because I've got some arbitrary CAD in there. I didn't talk much about the early boundary. I keep calling them early boundary conditions. That's a wrong term. There are certain areas where you would certainly want to use something like the perfectly matched layer. But if you look at what we've done with the evolution of these different boundary conditions, look at this example of a reflector antenna that has two feed horns. If we run this entire solution with an air box that has a perfectly matched layer boundary on it. My number of unknowns is about 7.7 million. It's using 137 gigabytes of RAM, and it takes about 2 hours and 15 minutes to solve. If I implement that with a FEA region, the benefit of FEA is that I'm no longer restricted by this rectangular box of my PML. So now I can get creative of the space that I can cut away. And because I did that, I was able to get my number of unknowns. I just simply have less mesh out in that space to consider, and I'm still getting my accurate simulation. So my number of unknowns comes down, which means my RAM also comes down, and my solution time has gone down to under 2 hours now. Now, if I look at separating out into multiple FEA regions, in the third example on the bottom, I've got 3 different FEA zones. I've got the reflector antenna that has this conformal FEA region around it, and then I also have the 2 excitations, the horn antennas, the feed antennas, are also in their own FEA regions. So now all the stuff in the middle has been cut out, and my number of unknowns is now down below 1 million. I'm looking at 18 gigabytes of RAM, and I'm solving that problem in just under 30 minutes. Finally, on the top right, I can eliminate my FEA region completely and just call it an integral equation region for that primary reflector. And now, since I'm only invoking the moment method solution on the surfaces, I don't even have to solve for the FEM air around the reflector itself. And that's how I'm able to get this thing down to just 5 gigabytes of RAM in less than 6 minutes. Okay, so I'd like to move into the asymptotic solvers now and talk a little bit about how we link those with FEA region as well. So a physical optics technique is also has a goal of solving currents on scattering bodies as well. It's just doing it differently. I can look at my currents that are established from some source, and I can calculate my H field and my E field in the lit region. Nothing is going to show up in the shadow region. For a physical optics solver, it's only able to solve for things that are actually in the lit region. For a lot of applications, that's perfectly fine. So here's a good example of hybridizing 3 different types now. I've got finite element solution with FEA boundary for my feed horn. For my subreflector, this is a dual reflector, I guess a Cassegrain type system. It's probably not a Cassegrain. It's a dual reflector system. For the small surface, we apply an integral equation technique. But for the larger surface, we have an option of applying either the integral equation technique or a physical optics technique. And the benefit of doing physical optics is because it's a much faster solve. It's an asymptotic technique. And it's also large enough so that we're not violating some of the key principles of using an asymptotic code. And typically that means that your scattering structure is on the order of 10 wavelengths or more of the wavelength that you're solving. And as long as that's the case, then you can usually get by with it. And if you look at the example here, comparison of the gain pattern is pretty much dead on. But if you look at the difference in the runtime and the RAM utilization, it's quite significant, right? So just by switching that IE region to PO, excuse me, for my larger reflector, it really makes an improvement that way. So I can build off of physical optics and use something called shooting and bouncing rays, which is still physical optics at its core. But what it's doing is extending physical optics from just single illumination of the lit region by using geometric optics for multi-bounce. So it allows us to take some source and convert that to rays ultimately that are taking that energy and interacting with the environment and scattering until the number of bounces has been met. And we're painting those currents just like we were in a physical optics or even an integral equation, similar to what we're doing in an integral equation technique, to get those painted currents. And once those painted currents are on the object, we integrate all of the contribution of those currents coherently at our observation point, which could also be at the other end of a receive system for a radar system. With shooting and bouncing rays, we're actually able to not only extend it to multi-bounce to allow us to illuminate things that are in the shadow region, but we can also apply some advanced diffraction techniques on it. So in some of these examples, you can see we can implement creeping waves. So if you've got conducting bodies that are, convex, like something like an aircraft, sometimes the dominant mechanism for coupling onto other sensors on the airplane could be through those surface currents that are generated. So we can invoke creeping waves. We can also borrow from different types of asymptotic solver technologies like uniform theory of diffraction and include what we call diffraction rays. So the name of the game for an SBR simulation is to paint as many possible currents as we can and be mindful to not double count those effects. And the more currents that we paint on that scattered geometry or environment, whatever it might be, the higher the fidelity our simulation is going to be when we look at those solved results. And it's extremely fast. You can solve a problem like this Learjet example, or at least some commercial business jet example, in about 3 minutes on a laptop computer that uses about 1 gigabyte of RAM. Quick example of how we can hybridize these different, even asymptotic techniques. Shooting and bouncing rays, in and of itself, would not have the ability to predict diffraction behind some blocking structure. But since we borrowed uniform theory of diffraction techniques called UTD rays, we can now illuminate the edges of that metallic object and evoke new rays that are the so-called Keller cone rays that are going to deposit additional current in those shadow zones that otherwise wouldn't be there. The example that you see of these two plates, without UTD rays, you wouldn't have any diffraction at all showing up on that bottom plate. It's the ability to be able to diffract and then allow that multi-bounce to take place from that point as well that helps improve the fidelity of the simulation. All right, so what does all that mean in the context of a radar simulation? I just walked you through kind of a very detailed simulation of antenna elements and finite elements. I explained how you can take that technology and extend that with other simulation techniques to be able to solve larger environments using this hybridization approach. And that's important because we're after things like radar scenes. So I'm going to the completely other side, I guess, of the scale now by looking at how we generate something like a range Doppler map. So in this example, it's exploiting a lot of the capability that we talked about. If I look at this long strip, that's basically just a chunk of road that we're simulating for this dynamic scene. If you look at the antenna patterns down here in the bottom right, those are associated with what we call the ego vehicle. So that's the vehicle that we're driving, either our autonomous system or the one that has ADAS technology on it. So now these array patterns might be coming from that scale-up simulation that I showed with HFSS and different techniques. So these could be radiation patterns for my transmit array and my receive array. And that establishes my channel. If I have a transmit antenna and I have, in this case, just a 1x1, a transmit system and a receiving system, what I'm looking for is sending my signal out into the environment and looking at what comes back. That's S parameters. Just like the S parameters that we ran with that dipole antenna, and when we copied two dipole antennas, the coupling between that's ultimately coupling. So if I can monitor the coupling across these dynamic scenes, and I can transmit the signals at the right time, hold on to those signals, and process them in accordance with all these different radar principles, I'm able to get meaningful information out of it. So in this example, we're going to do a range Doppler map that has my ego vehicle starting out at 30 meters per second. In front of it, I have a semi-truck that's moving at 35 meters per second. Same direction, but it's moving away relative to the ego vehicle of 5 meters per second. Now in front of that, I've got this pickup truck that is also moving even faster than the semi-truck. It's moving at 40, so relatively speaking to the radar system, it's going to be moving at 10 meters per second. And what's unique about this is that the radar vehicle, if you look at the front view of the radar, it can't see that vehicle at all. So if I'm relying, in this example, if I'm relying on cameras to make decisions, then this is an example of why radar is beneficial to be used in conjunction with cameras. This is the type of thing that you would not be relying on a camera system to do. So it's completely hidden from view in this case. So we simply can't see that pickup truck. The other things that you may have noticed by now, we've got guardrails that are set up. So these are some, stationary scene features that you would expect to see. And then you also see way off in the distance, here comes this incoming car that's moving at 30 meters per second in the opposite direction. So negative 30. So relatively speaking, it's going to be 60 meters per second in the other direction from that ego vehicle. And if you look at the scene size, we talked about finite element solution being kind of like dozens of wavelengths, ballpark. You're not going to solve this problem with the finite elements solution alone. So we need to use those different techniques, integral equation, and in this example we relied heavy on shooting and bouncing ray. So what you're going to see in the animation that I'm about to play is the range Doppler map that we generate is basically looking at downstream range. So I'm looking at about 250 meters in front of the ego vehicle. And I can see my Doppler velocity is going from negative 60 meters per second to 60 meters per second. So all of the things that are in my scene are going to, they're all limited to within these velocities and these ranges, which I've dialed in basically from my radar specifications. So when we put this in motion, you're going to start to see these things moving around. You're going to see the road return that's showing up at 30 meters per second. So that's reflections off of that asphalt road that is always going to show up as a relative velocity. Right down the screen, you're going to see moving at the same speed of the road return is going to be my guardrail. And you can see it gives a pretty significant response because that guardrail is like what we call the W channel. It's basically a corner reflector, which give huge responses. Way up in the distance, also moving in that positive relative direction is that small signature that's coming from the automobile. So that's the incoming car that was moving in the opposite direction. Over here, in the negative Doppler velocity, I can see these large blobs of scattering objects. The first one is showing up right here centered on 5 meters per second. And notice it's got lots of different, what we call scattering centers. And that's because the information coming off of that semi-truck is not just seeing the back door area of the trailer. Radar, the scattered signal is interacting with the wheel wells and maybe with the cab of the truck, and they're all showing up with different signatures. And then notice right here, this little blob out here that's 5 meters per second faster than the automobile. That's the thing that we couldn't see with the cameras. So if I put this thing in motion, I'll just let it loop for a minute. You'll notice that my angular velocity goes to 0 as we start passing through these objects, which is why you start to see that taper of the objects. That's to be expected in a radar system. So as my ego vehicle is going through the guardrail, you'll see towards the end it just disappears. And so does my oncoming vehicle. They pass it around at around the same time. You can see the relative speed between my semi-truck and the small pickup truck in front of it. They're starting to separate in space. So there's lots of simulations that's taking place here. So it's all based on how you set up your radar system, what your pulsing is going to be, holding on to that information, and being able to process it properly to be able to get something like a range Doppler map. So the last thing I'm going to end on is a quick setup of what we call I'm going to skip past that just in the interest of time and go through this demonstration of how to set up what we call a range profile. I'm switching analysis types to a shooting and bouncing ray type now. And I'm going to use something called 3D components. 3D components are a really convenient way to package. Think of HFSS models within HFSS models. So this thing that I just brought in, I guess the Mustang, it's got materials and geometries already set up. So I only have to set this up once if I want to start replicating this in a scene. And now I'm using my different ACT toolkits to be able to set up my simulation parameters. So I'm using something called the radar pre-processor, and I can set basically the size of the image that I want to create here and my range resolution. So what I'm saying is give me an image that's going to be about 50 meters. Excuse me. And I want to be able to resolve the difference between scattering features of any object that I'm simulating to within about 1/4 of a meter. And when we do that, the toolkit automatically sets up some of the HFSS parameters. So in this case, I'm using an incident wave. That incident wave has a polarity assigned to it. And I can see in my setup, if I double click, this is a 10 gigahertz simulation, but it's got a starting point and an end point below and above that with the appropriate amount of samples. So as long as I get my S parameters for my transmit and my receive system that are going to be spaced appropriately, I hold on to that information, and then I'm going to evoke some post-processing routines, and I'm basically doing FFTs of that sampled S parameter data. And now I'm able to take that frequency domain collection of real and imaginary parts of my S parameters, and I'm able to generate what's called a range profile. So there's my -25 to 25 meters means I'm looking at things that are in front of that vehicle as well as things that are behind that vehicle. And I can see centered right there in the middle where that Mustang was is that collection of scattering responses that I'm getting from that radar illumination. So that's one of the key elements that you're going to use and hold on to when you start building these range profile maps, or I should say a Doppler map, are collections of these range profiles. Excuse me. So now I'm going to change the scene a little bit by bringing in yet another vehicle. So in this case, we're going to go bring that pickup truck that we looked at earlier. And I can place that, it looks like in this example, it's about maybe 10 meters away. My simulation is already set up. So I can just rerun that same setup. I've got my plane wave illumination. And now all interactions that take place with the vehicles in presence of each other are going to be represented in that response that I get to feed my algorithms that are going to help me make decisions about what it is that we're looking at. So this solution is extremely quick. Remember, it's 10 gigahertz centered, and you saw 200 individual simulation points that were being done. So it's not the kind of thing that you would be doing without something like SBR. So once I get my real and imaginary response, I can go back to my toolkit, and we're going to generate a new range profile that characterizes the new scene. And it's got similar features of what you saw with the original one, but you can see there's some additional stuff there, right? So it's picking up about 10 meters away. You'll see these new scattering centers that are all correlated to that automobile. So if we repeat that process over and over again, then those are basically corresponding to what we would call a coherent processing interval for a frame of a radar system. So when we went through the animation of the dynamic scene, every one of those updates was using a number of those range profiles that were all stepped in that dynamic scene and then processed and then moved on to the next frame to be able to do that. So I think I made it right on time. I hope that you got a feel for how, our vision of what we see for using simulation, and I think this was very real in that we showed simulation being used in one modality of sensors all the way down to the basic sensor itself, how we can solve very complex sensors with analysis. We can run very complex scenarios, evolving into closed loop simulation for all sensors to be able to help make decisions for autonomous vehicles. And I hope you got to see that HFSS is actually pretty easy to use. I was able to put some, even though there were simple models, I was able to bring in models in real time and construct things pretty quickly. And with these add-ons of different hybrid techniques, like the shooting and bouncing ray technique, using things like 3D components, it's really doable to be able to start building very complex scenes all the way down from the elements of the radar to dynamic vehicles moving with respect to each other as well. So thank you for your time.
And just a quick thank you to our viewers again for coming, and thank you, Jason, for that just phenomenal overview of simulation for autonomous vehicles. Thank you. We don't call him the Bill Nye of Ansys for nothing. Okay. Well, thank you guys for tuning in. Make sure to like the video, share with your friends, and subscribe to Ansys Tech Tips on YouTube for more videos like this. And have a nice evening. Thank you. And so now that we're offline, we can answer questions and get to know you a bit. We have a small audience, right? So, yeah. So you guys are both.